Hello. Today we'll be going over Waterloo Farming Electric's powertrain setup, in particular motors and motor controllers on our Formula Electric vehicle. This will be a fairly high-level overview. We won't go into the nitty-gritty details, but it's, I think, a good idea to go over from the basics what a motor is, electric motor, how it works, how a motor controller works, and how it's integrated into our high voltage system. So here's a high-level overview. We have our motor controllers, which are experimental Sevcon Gen 5 size 9s. And we have our accumulator here, and we also have our MRAX 208 motors. So our accumulator outputs high voltage DC current of a maximum of 294 volts, and it gets inputted as DC into our motor controllers. We also have low voltage connections, which connect from our accumulator to our motor controller with things like CAN and our interlock loop for communications and safety control. Our motor controller, we have two of them actually, and they each connect with 3 phases to each of our motors. So we have two motors, two motor controllers. Each motor controller connects to one motor with the 3-phase cables. So this is a picture here of our powertrain system. Not pictured as the accumulator, but outside of the accumulator, you can see there are these 4 orange cables. The 2 on the left are our I believe, negative connections, so negative DC bus connections, and the right side are our positive DC bus connections, and they go and connect into our motor controllers. And it's not pictured here, it's difficult to see, but 3-phase cables come out of each and connect to our motors. You can see our motor controllers are these large gray boxes, and our motors are these smaller black cylinders. And the black cylinders, the motors, connect via sprocket ratio to our half shafts, which connect to our wheels. So the motors we use on our vehicle are MRAX 208 motors. They're 3-phase AC motors. And I'm going to quickly go over how AC motors work. So I won't go over in too much detail of how they work. I don't think a deep understanding of how the magnetic field is really important for what we're doing. I think it's helpful, but just an idea, going over some terminology so we can all have common understanding here. Okay, so effectively, when we're dealing with a motor here, there's 2 main parts. There's the rotor and the stator. The way I like to think of it is the rotor rotates, the stator is stationary. So the rotor is a winding that rotates in the motor, and the stator is stationary and essentially induces a magnetic field to move our rotor. Now, there are multiple different methods and topology of motors, but this is the general idea. We induce a changing AC current in our field windings, and that produces a magnetic field. This is known as Faraday's law. Changing AC current field windings induces a magnetic field. The magnetic field then induces a current in the rotors. This is Faraday's law. So changing magnetic field will induce a current into the rotor. The induced currents in the rotor generate an opposing magnetic field to the field induced by the field windings. So our field windings induce a magnetic field, and then induces current into the rotor. The rotor generates an opposing magnetic field by these induced currents to oppose the field generated by the field windings. And then these opposing magnetic fields cause the rotor to rotate. So it's not a perfect explanation. There's different ways at which motors actually work, but that's how I like to think about it. And I think that's like a good general understanding of how motors work. You have your field and your rotors. So your field windings are in your stator, and your rotor windings are in your rotor. So there's 2 real types of motors we're probably going to be talking about. Our permanent magnet motors are sort of self-explanatory. Rather than having a tremendous amount of flux windings, so you can generate a magnetic field through your flux field windings. Um, Rather than doing that, you have a permanent magnet installed in the motor, which is constantly generating these magnetic fields. And then you still have some flux windings, so you can modulate the magnetic field a little bit, but you really have this large magnetic field generated by the permanent magnet. And this allows for pre-excitation of the magnetic field. There's many reasons you would use permanent magnet over induction. We won't go over that, but the general gist is permanent magnets more expensive and they're higher efficiency, and they're actually also becoming more popular. I know Tesla is beginning to use permanent magnet motors, and we also have our induction motors. So that is, there's no magnet installed. You only have your magnetic field induced through your flux windings, your field windings, and that gives you complete control over how your magnetic field works, but you probably will lose some efficiency because you don't have this very powerful permanent magnet. So it's cheaper, but it's larger and heavier. Yet again, it's an oversimplification, but general gist of it. So current motor we use, MRAX is used throughout the industry. For hobbyist parts, most EV companies will actually produce their own motors. So Tesla makes their own motors in house, but MRAX is like fairly well known in Formula Electric and smaller companies. It's a permanent magnet motor. We get a peak of 68 kilowatts out of it and 140 newton meters, and continuous 41 kilowatts and 80 newton meters. And this is shockingly strong power density. So it's only 20.8 centimeters in diameter, which is quite small. When you actually hold it up close, it's a very small, compact motor that obviously induces an incredible amount of power. For reference, in the Michigan Formula Electric competition, you're only allowed to output a maximum of 80 kilowatts at any point in time. So with one motor, you're hitting 68 kilowatts peak. You're getting close to like the legal limit of the competition. And a 228 will probably overpower that. We have two MRAX 208s on our vehicle. So theoretically, that's a peak of almost 140 kilowatts. So we could definitely are not allowed to hit that, but it shows you how power dense these are. And the MRAX motors come in various varieties. So there's the low voltage model, medium voltage, and high voltage. We're using the medium voltage model, the MV, which is rated for 350 volts, and we're a bit derated by that. Our maximum pack voltage is 300 volts, so we're not actually hitting the maximum voltage of our motor, but that's fine. We're not too concerned about those losses there because really more voltage allows us to spin it faster, and we're not too concerned about that. So our motor controllers we use are the Sevcon Gen 5 size 9s. What is a motor control? I guess that's what we should probably start with. Is the idea is we have an AC motor. It needs AC current. We have a high voltage battery and it outputs DC. The AC motor, as I described, requires a AC current as it requires a changing current. Per these electrical laws, you need a changing current to induce these magnetic fields. So we need a shim layer, some sort of connection to convert our DC battery power to AC motor power. And we need to be able to use this to also control the torque and speed of our motors. So the term that is used in industry is an inverter. What an inverter does is it refers to the specific process of converting DC into AC. So oftentimes it's used interchangeably with motor controller. For example, at Tesla, they don't call it the motor controller team or the board, it's the drive inverter board. So it's sometimes it's used as an inverter, sometimes motor controller. The general gist is DC, AC. This is a hypothetical inverter using MOSFETs. You couldn't just put this down and it would work. There's a lot of deep technical skill and knowledge that goes into designing an inverter. It's a very difficult process, but this is the general gist of it. So for those who understand FETs, I'll explain this diagram. For those who don't understand how FETs work, essentially you can just view it as voltage controlled switches. So we have our high voltage here, our ground here, and in our phases, we want to create an AC current. So what you do is you turn on and off each of these switches at certain PWM frequencies to generate an approximated sine wave. So if I turn on A1, it will connect 300 volts through our FET here to phase A. When I turn it off, it's high impedance, so there's no voltage along this line. And when I turn on A2, it will bring ground connected to phase A. So effectively, there's like strong inductance and capacitance, so it's not going to actually be a PWM wave. It's going to be approximated into a sine wave. And we do a whole bunch of math and complex transforms to yield these results. So this is sort of an example, a cool image, which I think kind of resonates with me. Is here's an example of how you would modulate your PWM signal to sort of get the average voltage sine wave. And here's like an example of how the current would look. You'd have like little vibrations because of the switching of the FETs, but generally you're getting a motor current sine wave. So yeah, this is set up in a push-pull configuration. And one thing we got to be careful of is don't have two on at once. Otherwise, you're generating a short of 300 volts down to ground. Not good. Piece of terminology we use is something called the switching frequency. So how often we change between toggling A1 and A2 or B1 and B2 is called our switching frequency. So basically how often we switch the FETs is our switching frequency. It affects how smooth our sine wave is. So generally, a higher switching frequency is considered better. Your motor will like higher switching frequencies. So with higher switching frequency, you're gonna get less current ripple, less issues because of this like sort of jagged edges on our wave, and it's gonna be more efficient in that way. However, higher switching frequencies will result in higher losses on your motor controllers. So the faster you switch your FETs, the more heat is generated, and the higher thermal load on your inverters. Sometimes companies will attempt to move thermal load from their motor controllers to their motors by changing the switching frequency. So if I increase my switching frequency, there's going to be less thermal load on my motors and more on my motor controllers. If I'm switching them slower, there's going to be less thermal load on my motor controllers and more on my motors. But yes, as I said, motor controllers are actually very much more complicated. There's a bunch of filtering and complex control logic which goes into it, which we won't cover here, but it's just a general overview. Inside each motor controller or inverter, as I said, I showed above with FETs, there are these voltage controlled switches. And the inverter switches are constantly like being changed and improved to improve higher efficiencies, especially with the advent of electric vehicles. So this is a good diagram, I think, of like when to use each switch and sort of like how the industry has progressed. So we're dealing with switching frequencies in greater than 10 kilohertz. If we're going below to things like 2 kilohertz and below, you're going to get very large current ripples. So we definitely have to go higher than that. And we're also dealing with a fairly large voltage of approximately 300 volts or more. So if you look at this diagram, thyristors, very cool device, but we cannot use them at all. GTOs, certainly not. What we're looking for is in the IGBT to MOSFET range. And you could see that the MOSFET range has very low current that's allowed to pass through it, but they work at very high frequencies. IGBTs are more general purpose. You'll typically see IGBTs used more for these high voltage switching. I do know Tesla has been experimenting with silicon carbide FETs, so that's a new advent in inverter innovation. I believe because of higher switching frequencies and lower losses due to the on-state resistance. But IGBTs are more common, they're cheaper, and they're generally just like more robust and used. So that's great. We have our inverter, we can make an AC sine wave. But around our inverter itself, we have the actual motor control. So built around the inverter, we want to be able to control torque, speed, all the various components of our motors. And our inverter does this by changing the amplitude of the output as well as the actual frequency of the sine wave. So our inverters will take in typically over CAN for automotive applications, a bunch of parameters, and then output the appropriate frequency and amplitude of the sine wave based on that. So we apply things like a torque limit, speed limit, power limit, what torque we actually demand, inverter temperature. All these things are things we can like get from the motor controller and send to it to control it. I won't go over too much about our Sevcon motors, but generally we can do between 2 and 12 kilohertz. This is actually pretty low. I do know MRAX motors to get good current ripples, you need in the tens plus kilohertz. I think the 348s want something like 100 kilohertz to get reasonable current ripple. But also, if we're not too concerned about current ripple, this is a fine switching frequency, and typically you're dealing with around this range for small automotive cases. Yeah, so it's all over CAN. Software isn't great, but it is what it is. And yeah, so some people have asked in the past that I've done this presentation, why do we have two motors? Why aren't we using one? Almost all teams we've seen use one rear motor. I've seen teams that had hub motors in the past. Our team has done hub motors in the past, but we have two rear motors. The benefits are we can do torque vectoring. So this is actually very cool and fun project. We actually have torque vectoring on the vehicle right now, and it tremendously improves our cornering as you can effectively swing the vehicle one way by spinning one motor very fast on one side of the vehicle compared to the other while you're turning. So our torque vectoring means as we turn the steering wheel, one side will spin faster than the other, which is very helpful. The drawback is it's more complicated and there's more failure points. So packaging is difficult, and putting it all together, and it's just double the components means double the complexity. You're more likely to have one inverter fail, but it does provide a somewhat of a performance advantage, and it is just pretty cool to have torque vectoring on the vehicle. So there are a bunch of things I didn't cover in this section. So how the motor controller resolver works. I could have talked about how to actually control switching frequencies to move our thermal loads, our HVIL, torque vectoring, all these various topics. If there's requests to do them, I can do them in the future. But for now, that is it for the powertrain presentations. Thank you for listening. As always, you can view these pages on Confluence, and there's a ton more documentation on Confluence. Thank you for listening.